First of all, I welcome all people in this event. In this video, the results of the research entitled Determination of Radiative Characteristics of Carotenoid-Producing Microalgae are presented. This research was carried out by Luis Ángel Castillo Cruz and Neri Jocelyn Carmona Asensio, and directed by the doctors Hugo Joaquín Ávila Paredes and Patricio Javier Valadez Pelayo. The content of this presentation is as follows. Number 1. Introduction. In this part, the definition of microalgae and its application are briefly presented. Number 2. Project objectives. Number 3. Methodology. In this part, the experimental setup and the theoretical procedure are presented. Number 4. Results. And finally, number 5. Project conclusions. Introduction. Microalgae are photosynthetic microorganisms that from sources such as light, natural or artificial, carbon dioxide, and water are capable to produce microalgal biomass with a high level of metabolites. Among these metabolites, the carotenoid pigments have significant relevance. This has increased the development and optimization of new technologies to microalgae culture. These microorganisms are mainly cultivated in closed systems called photobioreactors and open systems such as riceways. The main factors to consider in the design and control of these systems are radiation transfer, hydrodynamics, mass transfer, and temperature and pH conditions. This research focused mainly on radiative transfer phenomena, with the objective to describe interaction of the light with suspended microalgae. The objectives of the project are the following. General, to develop an experimental setup and a methodology that allows estimating the radiative characteristics of the microalgae Chlorella vulgaris UTEX 2714. Particulars, to design and build an experimental system that allows the measurement of the different macroscopic variables, total incoming, transmitted, and scatter energy. To adjust precisely the methodology and experimental setup for estimating the radiative characteristics of the microalgae culture. Methodology. The initial point was the selection of the microalgae strain. Chlorella vulgaris UTEX 2714 strain was selected due to the following interesting characteristics. Duplication time of 24 hours, high biomass productivity of 0.11 grams per liter per hour, high content of total carotenoids from 5 to 58% of dry weight of biomass, and high content of proteins from 42 to 58% of dry weight of biomass. Now, to talk about the radiative transport in photobioreactors, it's necessary to know the radiative transport equation, which is an integral differential equation that describes an energy balance in a specific point and direction in the space. This equation has three main radiative parameters. Extinction coefficient, that represents the energy lost by absorption and scattering. Albedo, that representing the fraction of energy that is scattered after the interaction with a microalgae culture. And phase function, that describes the quantity of energy that incoming in the energy balance from different points. To solve the radiative transport equation, a stochastic method was used. This method is well known as Monte Carlo, that consists of the tracking of bundles or individual photons from their generation point of a light source until they are absorbed or scattered by suspended particles within the system. The algorithm to describe this phenomena starts with the calculation of initial position and direction. After that, the calculation of probable interaction distance with microalgae, or with the boundaries of the spherical container. In case the selected distance represents interaction photon microalgae, it's necessary to carry out a comparison between a random number with a value of albedo. If the value of the random number is less than the value of albedo, it is established that the photon is absorbed and saved this position. Otherwise, the scattering angle is calculated, and the initial position and direction are calculated again. On the other hand, in case the selected distance indicates interaction with the boundaries of the system, it is established that the trajectory of this photon is over. From this point, the experimental setup and estimation of each radiative characteristic are presented. In this figure, the experimental setup was designed and built at the UAM Iztapalapa facilities is presented. The parts of this setup are a LED as a light source adapted to a dissipator heat, two collimators with a length of 15 centimeters, a Pyrex glass spherical container, and an optical sensor. To estimate the specific extinction, it's necessary to carry out normal transmittance measurements with and without suspended microalgae. These measurements are defined as I and I0 respectively. To use the experimental values of this measurement, it's necessary to apply the Beer-Lambert law. That is a particular case of the radiative transport equation. The use of a second collimator helps to eliminate the quantity of scattered energy that could be detected by the optical sensor. And with this is possible to simplify the radiative transport equation to Beer-Lambert law. Results of specific extinction coefficient. Now, in this figure, it is presented experimental values of specific extinction coefficients at different biomass concentration. It is possible to see the value of this radiative characteristic is independent of the biomass concentration, with an average value of 1.6 square meters per gram. The value of the specific extinction coefficient depends on the particle size, and this could change with the formation of agglomerates that can form when the concentration of biomass increases. This phenomenon is depicted in the figure on the right side, in which two cases are presented. Number one, increased biomass concentration that produce agglomeration, and as a result of this, the value of the extinction coefficient can change. In number two, in which the biomass concentration increase, but the value of the specific extinction doesn't change. The experimental determination of the second radiative characteristic, now as albedo, was carried out under the following experimental conditions: homogeneous mixing, axisymmetric radiation intensity file, and optical thickness less than 1. In addition, the albedo was estimated under the supposition that established optical thickness value is equal to an experimental variable defined as phi that represents the fraction of energy that leaves the system. The experimental measurements carried out were the transmitted energy, point where the light beam is projected, and total scattered energy, 11 points equidistant on the surface of the spherical container. Results of albedo. The following figure shows the average albedo values of the suspended microalgae Chlorella vulgaris UTEX 2714 at three different biomass concentrations with an average value of 0.6. The average value of albedo were obtained through Monte Carlo simulation that used values of the extinction coefficient and phi that were previously determined experimentally. It is observed that, like the extinction coefficient, the albedo is independent of the biomass concentration under the formation experimental condition. For the experimental estimation of the last radiative characteristics called a symmetry parameter defined as G of the phase function, the same experimental conditions were carried out as for albedo. However, only the amount of lateral scattered energy was taken into account, because it is only seeks to observe the change in the dispersed energy by the microalgae culture as a function of the angular position. Finally, to estimate the value of G, the Henry-Christian phase function was used. Result of the symmetry parameter G of phase function. The following figure shows the percentage of the scattered energy as a function of the angular position at different values of the symmetry parameter. It can be seen that experimental measurements represent the blue circles follow the trend of the profile of the percentage of scattered energy with a value of G equal to 0.9. This indicates that the dispersed energy by the microalgae culture is mainly frontward. The figure on the right side represents the different angular position where the measurements were carried out. In order to obtain the different scattered energy profiles and to be able to estimate the symmetry parameter G, Monte Carlo simulations were carried out using experimental values of the radiative characteristics obtained in the previous stage of this methodology. The conclusions obtained in this project are the following. Number 1. The design and use of proposed experimental systems allow to obtain independent and rapid estimates of the extinction coefficient, albedo, and asymmetry parameter successfully. Number 2. The experimental setup was adequate to measure the different macroscopic variables in the system, incoming, transmitted, and total scattered energy. It was shown that the average value of extinction coefficient and albedo is independent of the biomass concentration. And finally, the phase function of Chlorella vulgaris UTEX 2714 can be described using the Hengy-Greenstein model, with G equal to 0.9. That's all for me, and thank you for watching this video.